Wouldn't it be great if we could walk through walls? Well, with quantum tunneling, we possibly could. Quantum tunneling, one of the most unbelievable scientific occurrences that have been discovered to this day. Quantum tunneling falls into the category of quantum physics. Quantum physics is simply the study of physical occurrences in very small things, such as atoms and the subatomic particles that make up those atoms. Tunneling is a phenomenon in which a particle, represented by this tennis ball, is trapped by a barrier, which will be represented by this glass bowl. And in order to overcome this barrier, all the particle has to do is appear on the other side.
It's crazy when you think about it, because this is something you never expect to happen in real life. That's because as the mass of a particle increases, the probability of tunneling occurring decreases.
Tunneling often occurs in the atom, more specifically, the nucleus of the atom. The barrier that protons and neutrons try to surmount during quantum tunneling is known as the Coulomb barrier. The Coulomb barrier is not a physical barrier like a wall or door, but more of an energy field that traps particles in the nucleus and prevents nuclei from fusing. In a way, the Coulomb barrier functions like a hurricane. The closer something gets to the eye of the hurricane, the more severe the storm becomes. But if you didn't know, once you enter the eye, the weather clears and there are blue skies. Similarly, the closer particles get to the nucleus of an atom, the more energy is needed to overcome the repulsion of the Coulomb barrier. But once a particle enters or exits the nucleus, the amount of required energy decreases. Since the Coulomb barrier has so much more energy than the particle, the only thing that will permit it to exit is to either attain an enormous amount of energy, or simply tunnel through, which would require no added energy. One area that tunneling occurs frequently is in radioactive decay. More specifically, alpha decay, which is a process in which an atom loses a package of 2 protons and 2 neutrons in order to stabilize the nucleus.
Now to talk about the probability of quantum tunneling occurring. We already established that the smaller the particle, the more likely it is to undergo tunneling. But when we shrink down to the atomic scale, how can we understand tunneling's probability? The reason tunneling even has a probability is because particles are in constant motion and have no definite location.
Well, let's start out with replacing the ball with this necklace in the shape of a wave. If you think of a particle as a wave function, we can have the highest point of that wave be the most likely spot the particle will be, and have the probability of the particle being in a certain spot decrease as the amplitude decreases. Because particles are constantly in motion, they can be in several places on the wave function, but if they happen to be in the location outside of the Coulomb barrier, then this particle will almost magically tunnel through the energy barrier without needing to attain any more energy.